Saab, who is always very much, I should say, positive for the new developments in the field of technology, because he is himself an engineer and knows about the technology. So he is always very positive for the legal metrology development, technological development of the legal metrology, and how we can do better in the fields. Sir, really, we are always thankful to you. You are always giving us your precious Saturday. I know that you have some other meetings also on Saturday, as usual in the government. Thank you very much, sir. We are always obliged. We thank you,
Thank you.
sir. Thank you, sir. Sir, today we have a very important topic about the air quality management, measurement, and instrumentation. This is a very important subject, sir. Actually, with the industrial development or industrialization of the society, we are getting more and more air, and the water are being polluted. So how the air quality can be measured, or what are the gaps in between industry, and what are the industrial opportunities? We have with us Dr. Shankar Agarwal, who is a senior scientist, principal scientist from CSIR National Physical Laboratory. डॉक्टर अग्रवाल, आपका वीडियो ऑफ है. विल यू प्लीज स्विच ऑफ योर वीडियो? थैंक यू सर, थैंक यू वेरी मच. सर, वी हैव विद अस डॉक्टर Shankar Agarwal. He is a well-known scientist in the field of metrology. His focus is on metrology for national ambient air quality standards, and basically he is involved in the precipitation gas standards and PM 2.5 samples and their calibration work, gas monitoring and analysis. He has done work in Japan and Taiwan for about 10 years. He has more than 110 papers, 1,000 talks, and many patents and the PhD students. Sir, we are very thankful to you. You are here, and he is also an award. He has also got an award for SciTech in 2013. Sir, we are very much thankful to you. You are here to let us know what are the requirements of the new developments, what are the technology, where the technology is taking us. Sir, actually, we are also planning to have this air pollution meter to regulate in the legal metrology, and with the help of National Physical Laboratory, we can plan over it, how we can do it, and what are the testing facilities or the calibration facilities have to be developed in the country. So with this, sir, I would like to request our Joint Secretary, sir, kindly speak two words so that and inaugurate this workshop. Please, sir.
Yeah, Namaskar. Thank you very much, Ashutosh Agarwal ji, and a very good morning to all the participants of this workshop today. And Dr. Shankar Agarwal, Senior Principal Scientist from the NPL, New Delhi. This is actually a very important topic, challenges and opportunities in air quality measurements and instrumentation. Now, every day we hear a lot about air pollution, and PM 2.5 and PM 10 are the common parlance discussions which the common man also wants to understand. But what is, I can possibly tell what our minister is wanting is the quality measurement systems and the equipment or an instrumentation which is available in the country should be very good, high quality, high precision measurement systems and instrumentation should be available. And that should be possible to possibly look at the air quality and other measurements also, which are more related to pollution issues nowadays across the country in major towns and cities. If you would possibly recall, there have been reports about the air quality index across the North Indian cities in the last few months. And usually this particular topic becomes more, conversant in the society, the newspapers, as in when October and November approaches in northern India, where the direction of the airflow and the wind is very different, and it allows a lot of smog and other pollutants to possibly settle in the air environment in these cities, northern cities. So I think there is a substantial opportunity for the industry to develop precision measurement and instrumentation, and the industry per se has been asked by the pollution control authorities to have maybe a measurement systems and these have to be under the certain parameters, be it our power generating units or be it any other industry and which is releasing effluents either in the air or in even water and ground. So this is a very contemporary topic, very important topic, and instrumentation and development of quality instrumentation is important. Today's topic, gaps in measurements or gaps in the instrumentation available, is of great concern, and I think we should have regular interactions about this with maybe the official bodies and developing countries where there is a great challenge about controlling air and other quality pollution. So I hope that today's deliberations in the workshop and the discourse and the lecture which will be given to us will be very elucidating and enlightening. It will give us a lot of knowledge about how the measurement and instrumentation is developing in the country, maybe internationally. I understand these would be some of the points which will be touched upon by the expert, and we would be delighted to listen to our expert, Dr. Shankar Agarwal. And with these words, I thank RRSL Ahmedabad and our LM division and Ashutosh ji for conducting this workshop today on this very contemporary and important topic. Thank you very much.
Thank you. Thank you very much, sir. Thank you for your kind words. Sir, I would like to request all the participants at the end of this workshop, we would like to take a photograph of all the participants so that we can share it on the Twitter handle. So at the end of this workshop, kindly be ready. We will on all these videos, and the participants have to start their videos themselves. We will allow them. Thank you, sir. Now, Professor Shankar Agarwal, please, sir, kindly share your presentation, please.
Yeah. Yeah, thank you, sir. I'm just sharing. Is it visible, sir?
Yes, sir. Yes, sir.
Okay. So, good morning, everyone. And I thank Dr. Ashutosh Agarwal for giving me this opportunity, and also Dr. Mathur Saab for inaugurate this session. So thank you very much. And of course, as Mathur Saab said, this topic is very, very important. And I made a very general talk so everybody can understand, and we should understand that how we are measuring and the instrumentation and what's the gap in instrumentation, and then what is the opportunity for us under the Make in India program, and also many startups can invest their interest or industries to fill up such gaps. So this is general, not very scientific talk, but very important talk. So what I will do, I will of course cover all the air quality measurements, what we are doing, and then I will also talk, at NPL what we are doing, right? Like in gas metrology, how we are making these standards, and also for calibration, we are doing some air quality measurement instrument calibration. So that I will talk a little, and also and finally the gaps. So let's begin with this. So in my talk, mostly I will talk about the air quality, ambient air quality, and source emission. So just to define or just to refresh you about air quality, the air quality means the state of the air around us. Good air quality means it's clean air, or polluted air means bad air, right? So polluted air. And ambient air quality means the quality of outdoor air in our surrounding environment. This is outdoor. Whenever we say ambient air means outdoor air, not the indoor air. It is typically measured near ground level, away from direct source of pollution, right? So source of pollution, what is the source of pollution? Source of pollution means any part or activity of a point, stationary or mobile source, that emits or has the potential to emit any regulated air pollutants or greenhouse gas. So we say that this is the source emission. I put some picture here. You can see This is bricklines. So you can see some source emission here, and this is coal energy power plant. So you can see again some smoke here. So it's also the emission source. So we have a many kind of source. This is the stationary source, but of course the mobile source as well, like tailpipe emission. When we run the vehicles, then we can see some smoke from the tailpipe. So it's a mobile source. So there are many sources. And like people say that in these days, people use electrical vehicles, and they say that there is a no pollution. Of course, at the site or at the point, there is a no pollution because this is electrical vehicle. But when we generate electricity, because when you purchase the car or vehicle, then electrical vehicle, then again we need to charge it, right? The battery needs to be charged. So when we charge it, then we need a consumption of electricity. So of course we are not polluting where we are running this air these vehicles, but where we produce the electricity, and if we are producing by the coal or some diesel sources, then of course we polluting that particular site. So again, there is a challenge that we need to find the sources. We need to find the way how we can get the clean energy. So government is also working for hydrogen mission. Government is also working for the solar missions to get the clean energy. And now government is already promised that India, by 2070, we will become the zero emission policy, the net zero emission. So all these issues, of course, targeting to the why we are doing all this clean energy, this, that, because we want that our pollution, our emission should be, very, very minimum or almost in the zero level. So that means these all things we need to measure very, very precisely. Otherwise, it's very difficult to make the carbon trading, and also how we can go for the zero emission. So these are very, very important point. So of course, everywhere the measurement is involved, and that's why the NPL, National Physical Laboratory, in the National Measurement Institute, National Metrology Institute plays very, very important role. So today the topic is air pollution. So here, this slide, it shows that the air pollution, it's very, very complex. For example, these are all sources, right? The primary sources. You can see this fugitive dust source where we got a lot of particles, PM 2.5, PM 10. And then mobile sources, as I said, that vehicular emission, again, we got particles, we got organic carbon, elemental carbon, ultrafine particles, which is very, very harmful for, of course, for climate and also for the health. So, and when we have a biomass burning, as Mathur Saab said, in Delhi NCR, we have a lot of biomass burning in October. So we got a lot of ultrafine particle and also gas emission. So because of this, Delhi always covered with the smoke blanket, and the situation is very alarming, especially in October, November. So again, this pollution has to be measured very, very accurately, and sometimes when we do not have such kind of high pollution, but our instrument says very high, and sometimes we have a very high pollution, but instrument cannot measure this thing. So we need a very, very good technology, especially for especially for Indian condition, because the Indian condition are different from other nations, and we have a very high temperature or humidity, and sometimes we have a very low wind conditions, and also sometimes we have a very low planetary boundary layer. So all these conditions needs to be considered, and then we need to make the instruments. So I will touch upon all these topics. Then we have stationary sources. As I said, we have the electricity plant where we generate electricity. So we have a VOCs, carbon monoxide, carbon dioxide, and many other gases, sulfur dioxides. And of course, we don't have this volcanic emissions, but we have a biogenic emission, natural emissions. So from primary emission, for example, when we have a tailpipe emission, from tail we can get a lot of carbon. We got a lot of carbon monoxide, we got a lot of sulfur dioxide or nitrogen dioxide. But as soon as these pollutants emit from the tailpipe, within few minutes they convert to another pollutants. Because in atmosphere we have a many ozone, we have a OH radical, we have a solar energy, solar radiation. So this got oxidation, they got many chemical reactions, so they form the particles. So these are the secondary pollutants, because primary means directly emitted from the source, and secondary means intermediate means, or secondary means pollutant can also form in the atmosphere. So both primary and secondary can make a lot of contribution to the total pollutants. And then they have effects. For example, they have visibility effect, especially when we have a pollution days. Then we have a very, very low visibility. Of course, we have a health effects. That's why we close some schools and other very important sectors. And then we have a material damage. We have a different impact on our plant and crop damage. Then we have a climate effects, and also sometimes the impact on our buildings. So pollution is important, and because they have a very complex reaction after their emission. So measurement is always is a very, very difficult and a challenging task. This slides also shows just one example. Then we have a PM 2.5, PM 10 in atmosphere, but because of the solar radiation or solar energy or OH radical, PM 2.5, PM 10 can convert to CO and CO2. So again, if we go for the carbon trading, then this CO2, which is not emitting directly from sources, but they are forming in the atmosphere, we need to calculate this CO2 also. So again, very, very complex, because we don't know how much PM 2.5 or particles can convert to CO or CO2. So this is the challenge when we go for the estimation of net zero. So in one of the recent meeting, people say that of course we can measure how much CO2 is emitting by this stack from the energy source or from this chimney, but after the emission, how much CO is producing, converting in atmosphere, or how much CO2 is converting, it's very, very challenging. And how we'll measure it, it's quite difficult. So we need to find some mechanism, some instrumentation, some measurement methods. So it's a challenge, and yes, really gap in this field. So if we want, it is very, very fundamental that if we want to measure very accurately, then these 3 points are very, very important. For example, instrumentation and sampling train, whatever we measure, whatever we use, should be EPA approved. EPA means Environmental Protection Agency approved. In India, EPA means our Environmental Protection Agency is Central Pollution Control Board, CPCB. So this instrument or train, whatever we use, should be approved. Then the sampling monitoring should be done following the ISO standard or protocol, or BIS standard, right? So if we have a BIS standard, we should use IS standard. Otherwise, if there is no BIS standard, then we can use the ISO standard and follow, and then we can follow the sampling or the monitoring method. Also, the lab or the measurement agency or lab, or that particular parameter should be accredited. So accreditation is also very important. If you have the accreditation, that means we are following perfect method, we have a traceability, everything. And when we talk about the traceability, that means whatever we use the standard for the measurement should be traceable. And sometimes it's not directly, there is a broken chain in the traceability. It's not directly linked with the NMI, National Measurement Institute system. So we need to check it whether it is really traceable or not. Sometimes I saw that many standards, they wrote that traceable to this. But if you look at if you see or check the link or chain, then it's not complete, and it's not really coming from the NMI or any NMI from the world. So this is the important point. These 3 points, when we meet, then whatever we measure would be very, very perfect and very, very reliable. So these are the 3 points which we need to focus whenever we go for air measurement or emission measurements. So for these all three, in India, we have a Bureau of Indian Standards. You know that BIS. So we develop some written standard, so that documented standard we can follow. For accreditation, of course, we have an NABL. So for measuring or for calibration or measurement laboratories, we need to accredit from the NABL, and also for the traceability, we have a National Metrology Institute, which is National Physical Laboratory. I'm from this institute, so I will tell about this a little. And then in ambient air measurement or emission measurement, we have a regulatory body, or our Environmental Protection Agency, which is Central Pollution Control Board, CPCB. So if these 4 pillars are joined together, then whatever we measure should be very, it would be very, very perfect, reliable, and then we can say that whatever value we are reporting is correct. So this is just one slide for our NPL, how it works, because you know that, and I think you all know very well, so I'm not going into detail, but NPL is a part, why it evolved, because of the meter convention, which happened in May 20th, 1875. And after that, we got 3 institutes, CGPM, CIPM, and BIPM. And this CGPM and BIPM, these 2 institutes are related with the all measurements. Whenever we go for any updation of the measurement unit, then we need to propose our proposal to these BIPM consultative committees, and then whenever they approve, we can follow it. So National Metrology Institute, like NPL, work on it. So whenever we need some intercomparison for traceability, like for if you want to measure PM 2.5, then we need intercomparison to get a traceability. So recently NPLI proposed that in India we have a problem of PM 2.5. So we need a traceability, because for size, for the flow, for others, yes, you can take the traceability, but directly for PM 2.5, first time we propose, and they just checked our capabilities, and they say yes, NPL India can do internationally this intercomparison. So recently in October 18, this last October 18, we had a meeting, and then we got this intercomparison. So India now lead on this PM 2.5 measurements all over the world to get the intercomparisons. So this is what we do with this consultative committee, and we get the traceability. So this is just what NPL is doing, and this is BIPM. You know that I'm not going detail, and I got a chance to visit several times this BIPM and propose our requirement, our intercomparison, our traceability requirements. And I'm not going into detail that, but just one slide here, that NPL, the NPL, the first brick of this laid down first by Pandit Nehru in 4th January 1947, and this institute was inaugurated by Patel Saab in June 20, 1950. So since 1950, this building is there, and we are serving to the country for the traceability especially. So just one information for you. And of course, because we are the National Measurement Institute, so as per the Parliament Act, we have we have this responsibility to maintain all the standards and traceability in India. And we do with the BIPM help, and also with the APMP help, and we maintain all these 7 base unit. But now in this all 7 base unit, we can maintain by the constants. So I'm not going in detail, because it's a different topic, how to use this all constant to maintain all these standard. But just one line that, yeah, we are maintaining all this standard and we have a traceability. Now, return to the air quality standard. If you look at the air quality standard in India right now, so this is National Ambient Air Quality Standard, and because Central Pollution Control Board is the regulatory body of India, so they have notified this air quality standard in 2009, right? So it's very old. Every 10 years we have to, we have to redefine this standard, but because of some COVID situation, we could not do it. And now there is a committee which is looking after this standard. So I'm the member of this. So very soon the new standard will be published. But this is still this standard, which is notified on the 18th November 2009 is working and stands. So we have in this, we have a 12 parameters. If you look at the parameters, first one is sulfur dioxide. Then second is the nitrogen dioxide. Then we have a PM10, we have PM2.5, ozone, lead. Lead means lead in PM10. Then carbon monoxide, then ammonia, then we have a benzene, then we have a benzoapyrene, then we have arsenic. Arsenic also in PM10, and nickel is also in PM10. So the important point is here, these 6 gases and 6 pollutant or 6 parameters are related to particulate matter. And particulate matter means, when we see the our atmosphere, we can see it is blue or dirty. So if we have a particles, you can say that this quality is bad. So particles are basically indicator, and in India, most of the gases, within the limits, if we can measure for yearly or monthly. So I can see, if you look the gas concentration is always under the limit. Like we have a limit of sulfur dioxide here is for annual limit. That means the annual concentration of SO2 should not be exceed from 50 microgram per meter cube, right? And for 24 hours, of course, not exceed from 80. So if just one example, if I look at the sulfur dioxide, yes, it is within the limits. And very few chances, they get the more than 80 microgram per meter cube for 24 hours. Otherwise, it's always below 80 for 24 hours and 50 microgram per meter cube, annual average. So, but if you look at PM10 and PM2.5 is always more than this prescribed limit. For PM10, it is 60 microgram per meter cube for annual, and for 24 hours, it's 100 microgram per meter cube. And on the other hand, if you look at here, PM2.5, it's 40 and 60. But as in the beginning, Mathur Saab said that in October, November, we got 300, 250 or 400 sometimes this PM2.5, very, very harmful. I will show you that they can go deep into the lungs because they are very tiny particles. So 2.5 micrometer size means if I look at my hair, the diameter of my hair is, or any person, it's about 70 micrometer. The diameter of hair is 70 micrometer. So if I cut my hair and I want to see it, sometimes it's difficult to see even 70 micrometer, right? But here I am talking about 2.5 micrometer. So by naked eye, it's difficult to see. So it's very tiny particle. And when we say PM 2.5 means it's not just 2.5, below 2.5, right? All particles from 0 to 2.5 covers by, when we talk PM 2.5. So 0.5 micrometer or 1 micrometer, it's very, very tiny particle and they can go deep into the lungs. So, you see that coronavirus, though the size of this coronavirus is 20 nanometer, means 0.02 micrometer. So this kind of fine particle can go deep into the lungs and very, very harmful for our health. So we will talk on this, and also these are the methods, right? These are the prescribed method here. So we have a very prescribed method here, you can see, and I will talk all this method in shortly so you can know, these methods are basically for the countries, those having a very less or low pollution level. But in India, we have a very high pollution. So sometimes I will show you our research or experimental data. Sometimes it's very difficult to use this instrument for correct measurements. Now, if I talk this gas parameters, for example, nitrogen dioxide, then sulfur dioxide, ozone, CO, carbon monoxide measurement, then what kind of methods they are. So if you look at this nitrogen dioxide, then we have a chemiluminescence method, right? And this is method Jacobs and Horsey's method. This is not, it's manual method, but the chemiluminescence is online method. So online means continuous method. You can just put the analyzer and you can see the values. So what this method is, so I'll tell you here, this is chemiluminescence method of NO2 measurement. So what happens in this, they have a one reaction cell. You can see the reaction cell here. Yeah, this is the reaction chamber, right? And then we can suck the air. This is the ambient air coming from this way and coming by this way and going in the reaction chamber here. Then we have an ozone generator here. So ozone generator can react, and when the ozone react with this, we got some energy, right? And then NO can convert to NO2. So this energy, what is producing here, chemiluminescence means some light is coming out by this reaction. Like here, I have shown here, you can see NO react with ozone and we got some light, H nu. So this light is proportional to the concentration of NO here. So in that way, we can measure nitric oxide in air. So this is indirect method, but very, very accurate. So the scientist got this, how to measure nitric oxide. This reaction is happening in the air also, in atmosphere. So when we have the thunders, when especially in rainy seasons, then all nitric oxide convert to NO because of the thunders. And in daytime also, when we have some spark or some ozone, so it can convert to NO2. So scientists looked and studied this atmospheric reaction, and based on this atmospheric reaction, they made this instrument. So it's a very, very simple instrument, just nothing, just one chamber here and one pump here, and then ozone generator, and then we have this photomultiplier tube. It is the detector, so you can see, and this is the display, and this is pump. But unfortunately, in India, nobody is making. Last, this standard, I will tell you that our EPA, that means CPCB, made this first regulation for NO2 in 1998, but still we don't have, if you look at this in 25 years, we cannot make this simple chamber and then this mechanism. Though we have a very, if you look at the IITs, our students, our brain, Indian brain, we have all infrastructure and all capabilities, but we could not make it so far. And if you look at the Indian government data, then we spend crores of rupees because we purchase this instrument every year, maybe 300 or 400. And one instrument cost about 10 lakhs rupees. So crores of rupees we invest and we give to the other countries, but unfortunately, we don't make it. So it's opportunity for industries to develop this kind of instruments. So this is just one example, and in all gases, if you look at SO2, if you look at carbon monoxide, if you look at ozone, nobody is making. Everybody is purchasing from outside. And if I see the mechanism, it's very, very simple, nothing. But yeah, so there is an opportunity, so we can make it. Similarly, for sulfur dioxide, you can see here, this is just like a briefcase. This is the instrument. We have a gas, we can suck because there is a pump, so we can suck air from here. Then The other gases we can scrub. Only SO2 molecules can go by this way. We have a UV lamp here. So SO2 molecules, they have the fundamental characteristics that they can absorb UV radiation at 215 nanometer, right? So they can absorb 215 nanometer this 215 nanometer radiation from the source, this SO2 molecules here, and then they can emit the fluorescence light that is little lower than this 215, 2 or 3 lines they can emit, and that this emission, the fluorescence light, can be detected by photomultiplier tube here. That's all, nothing else. And then this light, whatever they emit, is proportional to the concentration of SO2 molecules. So we can make some display or calculation algorithm and electronics to see how much, what's the concentration now. So this is the electronics. Again, nobody is making, there is no Indian industries which can make this. And we purchase again 300, 400 instruments every year, but and invest a lot of money, for their purchase. And one instrument, this instrument is a little expensive, or maybe 12 lakhs or 13 lakhs. So we invest it, but we could not make it so far. So again, there is an opportunity. For carbon monoxide, this is also the same. We have a IR source because carbon dioxide and carbon monoxide, they have a very good, the infrared region, they can absorb the gas. So they can absorb the radiation. So we have a sample here, the gas is coming here, and then they can absorb the IR radiation, and then this absorption is proportional to the concentration, and you can calculate by the Lambert's-Beer's law. It's very simple. So we say that this is carbon monoxide measured by non-dispersive infrared. So sometimes people ask me, what is the non-dispersive source? So non-dispersive source means the wavelength will not change. When we fix it for 4.6 micrometer, this is the wavelength of the absorption of CO molecules. So this will not change. If it is changing, that this is the dispersive. If it is not changing like this, then it is non-dispersive. So nothing, just 2 cells needed. This is a very small, maybe half feet or 8-inch cell. You can see the glass cell, and diameter maybe just 3-4 centimeter, the glass cell. And you have a pump here, so you can suck the gas. And then only thing is that technology. And I know that we have a very good brains, very good labs. We have a very good infrastructure, so we can develop it. And but some company needs to come forward to manufacture this in India. And again, this instrument, it has a huge demand, because I can see the government data that they need 300, 400 units every year. So yeah, there is an opportunity. Then ozone, the same. Ozone also have the absorption at 254 nanometer. So absorption is proportional to the concentration. You can just calculate by the Lambert's-Beer's law. So it is again very good opportunity that we can make a cell, and then we can see the concentration of ozone when we have a UV light source, because this comes 254 light needed. 254 nanometer light is needed to get the ozone concentration by Lambert's-Beer's law. So again, there is a chance. And we have because ozone is very reactive. So when we want to standardize, or we want to calibrate the ozone analyzer, then it is difficult to use the gas cylinders, right? Because it's gas cylinder, you can't fill the ozone in cylinders. So we have primary ozone standard. So primary ozone standard means again one analyzer which is traceable to other countries. So then we have the customer analyzer, so you can compare both and then make the calibration. So NPL having this primary standard of ozone. Sorry. Yeah. So now come to the standard preparation, because when we develop this standard, or when we have this analyzer on our monitoring stations, then we need to calibrate them. So, and what NPL is doing in that, so NPL has the gas standard preparation facility. So we have a gas preparation facility. What we do first, first we purchase the empty gas empty gas cylinders. You can see this is the gas standards. So what we do, first we evacuate them. We heat around 70 degree and evacuate them in very low pressure, like 10 to the power minus 3 millibar pressure. So we evacuate. So whatever VOCs or moisture inside we have, we can evacuate them, right? Because of the low pressure. And then the empty cylinder we can weigh. You can weigh first. And then, for example, I want to make a 10 ppm 10 ppm carbon monoxide gas standard. So how I will do? First, I will weigh this empty cylinder and then I will fill the appropriate amount of CO, and then I will dilute it with nitrogen dioxide. So in this way I can make. So this is the flow chart you can use here. So first of all, we need to planning like a 10 ppm CO. If I want, then I need to make the planning. Then how many concentration of pure CO I need. I need to calculate the mole fraction because I want to make 10 ppm CO in nitrogen, right? So all mole fraction I need to calculate. Then heating, evacuation of the cylinder. So I need to do this. Then weighing of the cylinder, empty cylinder, then filling of the component gas, because I already calculated how much CO molecules I need. So I need to fill this CO in the empty cylinder, and then filling of the mixing gas. Here is nitrogen. So I need to fill the nitrogen gas, then final weighing of the cylinder, and then homogenization and then validation. So homogenization and validation we can do. This is the final weighing of the cylinder. We use a double pan balance. So this is the difference, and this is the in which we are making the standard, because we want to nullify the buoyancy effect. So we use double pan balance. Then we can homogenize using this. So this is homogenizing system, and then we have GCs. So we can measure this if I make gravimetrically carbon monoxide 10 ppm, then I can analyze whether it is really 10 ppm or not. So once I ensure it, then I can certify the gas, this cylinder, right? So in certification, I can add the preparation, that means the gravimetric preparation uncertainty, as well as this analytical uncertainty, both. But one more thing is important, that because I am adding or diluting this CO with because I am making CO in nitrogen, right? So if there is some CO in nitrogen already existing, then I will be in trouble, right? So I need to check this, and if there is some ppb or ppt level CO present in nitrogen, I need to account for this concentration also. So for impurity checking, we have a CRDS, cavity ring down spectrometry. It can go or measure very low concentration, ppt level concentration. So we need to incorporate these impurities as well when we calculate the final concentration of CO in standards. So this is one example. Then we prepare a standard and put like this. So we give or we disseminate this traceability to many Central Pollution Control Board laboratories, state laboratories, also ISRO, and also many other government, and this Pune, there is a one emission laboratory, so we also, and also many accredited or accredited NABL lab, we also supply this standard. So they have the traceability linkage with NMI. Just one example, it's not like whatever we are saying is correct or not. So we need to intercompare our results with other NMIs through APMP and BIPM, as I said, just before. So this is, you can see for this is CO2. CO2 is very important for climate change or this climate issues. So people say that in these days the concentration of CO2 becomes very high, like 420 micromole per mole means ppm. So BIPM organized one intercomparison, and this is our value, you can see. And if you look at here, the most popular NIST value is here. You can see NIST USA, and NPL UK value is here, and all are NMIs, So NMI China is here. You can see they have a more uncertainty than us. So this is NPL, and you can see sometimes the other NMI, even NMIJ, this is Japan. Our values is much better than Japan. So uh, we have a capabilities, and we are giving this gas standards to the country, but because NPL is very, one institute, we have a limited manpower. So we want that more industries should come forward, get traceability from us, and then they can produce gas standard or gases for serving to the nation. So there is again opportunities for industries to make standards, gas standard, and serve to the countries, because NPL cannot cater all the countries, right? It's one institute. We have a very small gas metrology group, because you know that in NPL we have many divisions for different parameters, for different units. So it's not possible to cater all the country, right? So we encourage industries, the young industry man to come forward and establish the gas industries, and also the air monitoring, manufacturing work, and also we have many monitoring stations, but once we establish this, after that we don't care whether it is working rightly or not. So every time we need a maintenance of these monitoring stations. If you look at the government data, about 700 stations we have in India, but I don't know, if they are working very well. So even in our New Delhi, we have about 28 monitoring stations, but maintenance is an issue. So we need some industries, some bodies to come forward and make the training and make the expertise, and then they can maintain these standards. So these monitoring stations. So it's a huge gap and also opportunities. So this is all about the gases, instrumentation, and also the gas standard preparation at NPL. Now particulate matter. This is very, very important topic, and I will tell you about the particle matter health effects as well. So please look at, maybe very interesting for you. So if you look at this, I like this particulate matter because I work since last 25 years on this topic. So it's my and also my PhD topic. So I like this very much. So aerosol effects, if you look at the particulate matter, we also say aerosols, because aerosol means suspended particles in air, right? So they have a physical properties, they have optical property and chemical property. If you look at the climate effect, we talk a lot about aerosols, particle, their impact on the climate. If we say greenhouse gas, people can understand greenhouse gas can absorb the energy, so they can make the ground surface or surface temperature more, right? So because of this heating effect, they can change the climate. We can understand very well. Then ozone, is also the greenhouse gas. Then CO2 is also, methane is also. But how particles can, impact on our climate. So it's very important. If you look at here, this is one particle only. And if there is a one particle and it is the black particle, then it can absorb the solar radiation. Once they absorb the solar radiation, that means it can again heat the climate, heat the atmosphere, heat the surface or ground level temperature, right? So it is direct effect. On the other hand, they have the indirect effect as well, because you have the cloud, and when we have a solar radiation, what cloud will do? They can scatter light back to the space here, right? So that means the light is not coming in the ground. So cloud can protect the solar radiation to come to the ground. So in the other way, they can cool the ground surface. But when we have a particle in between the clouds, then cloud means water vapor, right? So water vapor can condense on this surface of the particle, because for condensation, surface is required. So when this cloud condense on the particle, what will happen? They will condense, and one condition or one situation will come when it becomes the drop. And once it becomes the drop, then you will get the rain. So once the rain will come, then what will happen? This cloud will disappear. So when this cloud will disappear, then what will happen? This direct radiation will come and then impact on the surface. right? So again, they will change the solar radiation budget of the surface. So this is indirect effect. So aerosol can make both effects, and it's depend on many, many parameter of aerosol size, of course, the scattering and absorption properties, and scattering and absorption properties also depend on the chemical property. If it is salt particle like ammonium sulfate particle, then it can scatter the light. But if they have the black carbon particles, like when we have a biomass burning impact, then they can absorb the solar radiation. So in Delhi, people say that I got a lot of problem because of the vitamin D problem, right? So when we don't get the solar radiation, because of the particle absorb all this, because of the black particle, we have a lot of biomass burning impact, right? On the because we have a lot of burning practices. We burn a lot of burning practices are our habit actually. So when we burn it, then we got a lot of particles, and these are all black particles. So when we have a black particle atmosphere, they have a fundamental characteristics. They absorb the solar radiation. So when they absorb the solar radiation and particular wavelength, which can which can which can help our body to form the vitamin D, we can't get it because of the high pollution level. So in these days in Delhi, most of the people have the vitamin D deficiency. So because of this particle, this is the already people studied, and I got a lot of material publication on that. That because of the black particle, we have a less solar radiation, and that particular the wave of radiation which can help us to get the vitamin D. So because of this, we got a lot of deficiency of vitamin D. So this is health effect, but health effect I'll go in detail here. You can see uh, inhalation health effect I am going to talk now. So this is our lungs, and these are the particles. You can see when we breathe, then the particle can go in this way, and if the particle size is very small, they can go deep into the lungs. You can see in this, the particle is coming, and the size is less than then they can go deep into the lungs. And when they go deep into the lungs, so they can mix with our blood, directly mix with our blood. So if the particle composition, say that they have the polyaromatic hydrocarbon or metals, and it's carcinogenic, then again it's a problem. So tiny particles, smaller particles are very important. Here you can see the simulation. This is the total particle concentration, total particle distribution. Here in the x-axis you can see the particle diameter from 1 to 100.1 to 10 micrometer. 10 micrometer PM10 particles here. It's a 100 nanometer particle here, and this is the total distribution, right? So how when we breathe this particle, so how they will go or distribute in our lungs, you can see. Yeah. So bigger particle can go up to our throat. Then if we increase the little amount in the lower side, then they can go to our lung. PM 2.5 particle can go in our lungs. And if we have a PM particle, PM1 particle, more smaller particle, they can go deep into the lungs. You can see here. And if we change a little and make more smaller particle, of course they can go deep into the lungs. So this is very important, and this just to show that when we cook in our home, then we have a very tiny particles. So we need a proper exhaust, otherwise yeah, it can create a problem. And also whenever we burn, whenever we do some combustion exercise, we got a very tiny particles, and these are very harmful. I have a many news cutting just for for your information. It is November 26, 2014. You can see in 5-6 years what we did in Delhi. There is a newspaper cutting, and it shows that Delhi choking on foul air, time to clean up, right? And then they say that the concentration of PM 2.5 becomes like 300 micrometer per meter cube. Then they say that it's alarming in November 26. As in the beginning, we said that in October, November, we have always have this kind of problems. So they suggested many ways how to reduce this in 2014. We made some progress, but again, if you look at in this is 2015. Again, we say that bad air. Delhi races ahead of Beijing, China. Delhi's winter course is back. You can see it's also in December 4th. So this is blue one is Delhi. So the same thing is happening here again. Then in 2016, Delhi government says that, okay, you can do what we can do. We can use the odd and even exercise. So we got odd and even exercise. The vehicle, we have a odd number, so we go for particular days. We have a even numbers, so we can go in a particular days. And then 4 agencies made the all. What's the happening when we use this odd even practice? Then what is the concentration of pollutants? So 4 agencies measured, and all 4 agencies made the different results. You can see Delhi government, they say that I can say here, claims more than 50% drop in air pollution level. Then Ministry of Environment and Forest, they say that data shows air pollution began peaking in January 3 onwards, but started falling from January 8. Then Ministry of Earth Science, they say that peaking from January 3 to reduce sharply in January 8 night 2 onwards. Then Environmental Pollution Control Authorities, what they say, despite very low wind speeds on days during odd even scheme, pollution fell those days. They say that it's going down, green one, and this one say no, either there is some effect or there is a no effect. So 4 agencies, 4 results. This is the problem. So what we will do? It is, आप क्या policy बनाएंगे अगर you have, this is because we don't follow these 3 points which I made in the first slides, that we have to have particular methodology, particular instrument, calibration, traceability, accreditation. They don't use, so you can't rely on this data. Anyway, so traceable, comparable data and information are essentially needed if you have this kind of things. Otherwise, it's difficult. So still, government cannot make odd even policies because they don't have a perfect results or confident results that, okay, you make this policy, you'll get this. So अभी 14 से तो मैं आपको दिखाया, in 14 से लेकर के and 22 तक, you have about 6-7 years, but still we are in the same level. This year also we had the same problem. And अगर हम ऐसे ही रहेंगे तो next year I'm sure that again we'll get the same problem.
Correct.
So air quality worst early in this year, you can see in 16th. So this slide I shows that they use these are measured using low cost air quality monitoring equipment. What is low cost air quality monitoring instrument? They don't have calibration, they don't have regulatory parameters, regulatory the permission, but they use it. And they say that one place here, you can see this one, they have a concentration or 104 microgram, or here you see here they have a 182, but on the other hand, just if you see this distance is less than half kilometer and they have a 1000 plus concentration of PM 2.5. It's not possible if you have this much of here you have a 400 and here you have 1000, just 500 meter distance. I know that. So this kind of panic you create when we can't say that which one is correct, this one is correct or this one is correct, because there is a no these 3 points are not followed in any of these measurements. So this is the issue. Then 16 again, why our northern plains are world most polluted areas, and Delhi is ranked 5th India and globally ranked 11. So it's create bad name of country if you make like this kind of measurements without using standardized protocols. And then this again, it's very recent one, 2018 comes now, you can see. So among India cities, among 15 most polluted. So media can write anything. If we have this kind of data, they can write. So I think the responsibility is from the scientist and from our regulatory body and our ministry, and we are the responsible for this, because we cannot control this kind of things. There is a pollution, I am not saying not pollution, but whether it is correct or not, measurement protocol is correct or not, whatever we are measuring is correct or not, is a big challenge now. Again, 2021, Delhi remains most polluted capital report. So every time we got this kind of report, but we are not coming to the one solution. And if I talk to the WHO, why you are making this kind of thing, so they say that, sir, you can see on our website that we say that we 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 write this because the from article from peer reviewed journal, whatever you published, we use this ground measurement compiled in the framework of Global Bureau of Disease Project. Some private agency making this without regulatory protocol. So we use this. And type of the data use, you can see in the absence of the annual mean, measurement covering a more limited period of the year were exceptionally used. So they just for say for if they don't have annual mean, साल भर का data नहीं है, so what they use when we have a October November very high data, so they use it. Where no urban means was available, the eligible city data were averaged, which is not necessarily representative of the city's mean air pollution. See, so this kind of data, different measurement method, if they use, they also use. So they have written on their website that this data, whatever we are reporting is based on this. So they are safe. But it creates panic and bad name of the country. This is the most panic thing and painful thing for me and for other you maybe. So it's not good. So we need to educate the people, and I just say that we need to ask our own people to come forward, make our own instrument which can work under our conditions, perfectly work on the our condition, Indian condition. So that's why NPL director said, the National Physical Laboratory says absence of calibration in India gives inaccurate results. This is in 2016, and then we tried very hard to develop our own system, and we got some success on it. So I'll take about this. So PM measurement and research, what we did at NPL. So first, just talk about the measurement method of particulate matter, how we are measuring it right now. And these are all regulatory methods, right? Regulatory means approved by our Central Pollution Control Board. So we have a three method of measurement. Number one is gravimetric method. Number two is tapered elemental oscillating microbalance, TOEM, and then beta attenuation. Here, this is beta attenuation, this is TOM, and this is gravimetric method. Gravimetric method is most reliable method. As you know, it's nothing. It's just we take the air from here. We have a filter here. So before sampling, we can weigh the filter, and after sampling, because we are taking air from here, we have a pump here. So air is coming by this way, and particles are filtered on the filter, right? So particles are depositing on the filter. So whatever mass we got on the filter, when we weigh filter before and after, we can get. And then how much air we suck, the volume of the air, we can divide. So we'll get the concentration, which is written here, microgram per meter cube. So this is very, very accurate because it's a gravimetric method directly traceable to mass. But the problem with this is, that, you can't get the data in one day, or in the online data or continuous data, because first you have to weigh the filter. So for weighing, you need to condition the filter at particular moisture. Then after sampling, again you have to do the conditioning and weighing. So it takes about 48 hours to get one data. So it's not online or continuous method. On the other hand, this beta attenuation is automatic method, and you can see you get the air here, and the working principle is here. We have a tape here, so particle can deposit on the filter, and we have a beta ray source here. You can see the source here, just black one. This is the beta source, and we have a detector here. So initially, whatever concentration of, because initially there is no concentration, so only filter is here. So whatever beta rays detector can detect, it's I0, initial intensity of beta rays. But after 15 minutes or 20 minutes, when we suck the particles can deposit on the filter, and then beta rays can be attenuated. थोड़ा सा beta rays कम हो जाएगा, because the particle can absorb the beta rays. So this attenuation, say it is now IT, after time t is IT. So initially is I0, but after time t is IT. So the difference between attenuation, difference between the beta rays is proportional to the concentration of particles, whatever we collect. So it's also very good technique, but we saw that this is not very good for when we have a very high concentration. I will show you some data. And this is taper elemental oscillating microbalance. So what we have here, air is coming, and this is the element which is oscillating by one frequency. But when we deposit the particle on this head, so the frequency will change, and then change in the frequency is proportional to the concentration of particles. This is also very simple method. But again, of course, we have many manufacturers of this gravimetric method or gravimetric sampler developer in India. About more than 30 manufacturers are there. But unfortunately, we don't have this any manufacturers who can make the beta attenuation, BAM or TOM in India. So in monitoring stations, as I said, 700 monitoring stations, we need PM 2.5, and also we need the same instrument for PM 10. So about 1500 instrument we purchase from the outside, and the life of this instrument is 5 years or maybe 6 years. So every 5-6 years we need to replace, and this is the just government monitoring station. But the same also we need to put in industries. So we have huge industries in India. You can see. So as per the regulation, we need this instrument. So it's a huge opportunity if we can make, and it's very simple. I will tell you, we did some work and we have a prototype ready in our lab, and we are looking that someone come forward, some manufacturer, so they can get this technology from us, so they can make a first beta attenuation instrument for India. This is just the sampling head. From this we will get PM 2.5, PM 10. Okay, so now we are here at the Ashutosh Saab. Can we take 5 minutes gap and then we'll come back?
No problem, sir. No problem. We can.
Okay,
Please.
so I think it's
Yeah.
So it's almost 1 hour. So
Yeah, you take your 5 minutes break. No problem, sir. We are here only. You please take your 5 minute break.
5 minutes and then we'll come back. I will tell you more interesting things now.
No issue.
Yeah.
No issue. You please take. Actually, sir, what we are you take rest.
Please tell me. Yeah.
No, I will continue, sir. Because, sir, what I come to know that even now we are having the nanoparticles in the air.
Right.
These of the plastic, even the plastic nanoparticles are entering inside the body, and as the kidney cannot filter them, they are directly mixing in the blood. And maybe that after some time we will be, because kidney has the capacity to filter of the micro level particles, not the nano level particles.
Right.
So I may be right or wrong, but I was reading somewhere, or somebody was telling me that this is a big problem, and maybe that after some time we will be having another type of cancerous problems in the people due to this plastic pollution inside the blood. I don't know how much it is correct. You may be the right person to put light over it. But you take rest. We will discuss after 5 minutes, sir.
Sure, sir. Sure.
Basically, these topics are very much required. And sir, we are thinking that we should have some industries which can start, or which can think over the manufacturing of these type of equipments in India. Most of these equipments, unfortunately, are imported one. And as he was telling that the life is of 5 years or 6 years, again we need again to change and all. And that's why there's a problem. We have to invest a lot of forex for all these type of equipments. And unfortunately, due to the equipments calibration, as these equipments are not calibrated, what we are observing, it is right or wrong, we have to be we are not actually correct. We have to think that these equipments are calibrated. In legal metrology, sir, these equipments are already covered under the, because these equipments are the measuring equipments, and we are planning to have the calibration procedures or calibration technology in the laboratories, so that at least the calibration of these equipments can be started, and we can get the correct results. Otherwise, it is like that a weighing machine of, let's say, 5 kg, and we are measuring the weight of 50 kg. So it is showing that how much it is showing, we are just taking that it is right or wrong. In the same way, the capacity of this measuring instrument of a pollution measuring equipment is, let's say, of 300 ppm, and we are measuring it 900 ppm. So how much it is giving, it is showing, or the results it is giving, we are not confirmed, we are not sure. Basically, the industry and the academicians and the R&D people, as well as the regulators, have to think over it, how we can develop a good system, air quality system in India. Because as we are staying in Delhi, and I don't think so that we feel any problem. Even I used to travel by two-wheeler on the scooter when I travel in Delhi. I never feel this type of problem when the people are saying that there is a lot of pollution, this and that. Because we have seen the pollution of 1997, 1995, 1992, when there was a lot of air pollution due to the buses and the taxis of the diesel. Right now, these type of pollution is not there in Delhi. So I don't know whether how much pollution is actually is there or not. I'm not aware of that. The technology or the measurements, how they are correct, because as he was saying that the four different testing facilities or the organizations have their, not the synchronized data. So we have to do something in the manufacturing, because as Atmanirbhar Bharat we are doing, and a lot of other things are being happening, and these equipments, I don't feel that these are very they need too much investment. We can discuss it with the scientist, and they are ready to help us. If few of the industries are interested to start manufacturing, we can directly have a contract with Dr. Shankar Agarwal Saab. He is a very nice gentleman, and certainly NPL will help the industry to become self-sustainable or self-reliant, who can manufacture these type of equipments. I hope that we will be having some more discussion on these topics. Some of the few participants have raised few questions. We will discuss them later on. But as far as video is concerned, yes, video, I don't know whether we will be able to share the video or not, but I think that presentation we will share after the program. When we will issue the certificates, every participant will get the presentation. I will take it from from Dr. Agarwal Saab, Dr. Shankar Agarwal Saab, and I will share it with the certificate. And at the end of the program, at 1 o'clock, maybe earlier to that, we will be having a photo of all the participants. We will allow all the participants to open their camera. They will be able to open their camera. We will take the photos and we will put it on this Twitter. I will request all of the participants to kindly retweet and like this tweet, so that the people should know that these programs are also being organized every week, and more and more knowledge sharing sessions can be organized. Over to Dr. Shankar Agarwal Saab.
Thank you, sir. Thank you. So, yeah, now, we talk a lot about PM technology, PM 2.5 standards and how we can measure it. And because this is given in our standards, right? National Ambient Air Quality Standard, particulate matter PM10 and PM 2.5. So we follow these three methods. So before I'm going, we go for a technology part. First, I would like to tell you when this National Ambient Air Quality Standard was first published and which country, they published this first National Ambient Air Quality Standard. So just a little history about the National Ambient Air Quality Standards. So like India, we have this problem now. You can see in last 15, 20 years that we got a lot of pollution problem. Before that, of course, in Delhi or big cities, we got some problem, but in small cities, we do not feel this kind of pollution problem, right? Similarly, in US and also in UK, London, they have a London smoke, or in US, they have the industrialization. So in 50s and 60s, they got a lot of pollution problem because of the industrialization, and they don't have emission control technologies at that time. So then US EPA, they thought that, okay, we have to control it, and we need to make some regulation. So first, National Ambient Air Quality Standard, they published in 1971, right? And you can see at that time they use only TSP, total suspended particulates, not the PM 2.5, PM 10. So TSP means total suspended, whatever, they don't have any size, they just use TSP at that time, 1970, because they don't have the technology to only measure PM 10 or PM 2.5. So this is US standard, and it is first published in 1971, April 1971. Then the first PM10 introduced in the world by US, and it is introduced in 1987. So it's very new. You can see PM10 they introduced in 1987, and then the first PM 2.5 introduced by them in 1997, and in 1998 we made PM10 in our regulation, and also in 2009 we made this PM 2.5. So after almost 10 years, after this 10 years, we made a PM10 in our standards. And then after 10 years, almost 12 years later, we made a PM 2.5 in our standard. So, before that, they don't have any perfect technology to measure PM10 or PM 2.5. So this is for TSP, total suspended particle. You can see this is the sampler. We use this sampler, it's like a washing machine. The size is like a washing machine. And then we have here, it's particles coming, and then here is the filter. So you can see the yellow particle which can stop here or deposit on the filter, whereas the blue one is the air. It's just the blue is air. So air is coming, filtered air is coming. So whatever particles we have in air, we can filter on our filter. So this is called the total suspended particulate matter. Whereas for PM 2.5 and PM 10, there is only these two technologies which are very, very common. One is the impactor and second one is cyclone, both based on the inertia of the particles, right? So impactor means how it works. We have a nozzle, you can see the nozzle, and then we suck air through this, and then after this plate we have a filter here, right? So what will happen when we suck the air, then because of the inertia of the heavy particles, they stay on the plate. This is the impaction plate, and then finer particle can go through, and then they can follow the air stream, and then they can deposit on the filter. So when we design this impactor, designing means the size of the nozzle, the distance of nozzle and this plate, and then flow rate. Then accordingly we can segregate the particles. So if we want to segregate PM 2.5 particles, then we have to design it, the diameter, then distance, and then flow. So more than PM 2.5 size particle will stay here because of the inertia, while the smaller particle can follow air stream, and then they can deposit after this impaction plate. Similarly for cyclone, it also works on the inertia. So gas is coming here, we are sucking here, and then we have a barrel here. It's a tube, inner tube. So air can move like this. So we have a centrifugal force. So now impaction, because of the bigger particle, can again hit here at the surface of the inner surface of the cyclone, and then finer particle can follow this, and they can rotate like this, right? So because of the inertia, the bigger particle can deposit at the end of this cyclone, and then particular size particle can go by this way. And when we put the filter here, we can collect. So these two technologies generally used to get the particle size segregation sampling, PM10 or PM 2.5. Here is again the particle is coming, and then you can see the blue one. This is bigger particle will stay here, whereas the smaller particle can follow their stream and they can deposit on the filter. And this is very typical nozzles or impactor. You can see the nozzles, and this is the impaction plate. And after this impaction plate, we have a filter here. And this PM 2.5 and PM 10, how we will say, because it's not the sieve. ये sieve तो है नहीं. So sieve means if you make the 2.5 sieve, जो छलनी होती है हमारी. So if we make 2.5 micron sieve, it will choke immediately, because 2.5 we cannot say even our eyes. So we cannot segregate the particle by sieving principle. That's why we use impaction or cyclone principle, right? So then how we will decide, how we will calibrate this instrument, how we'll check this instrument, how we'll test this impaction, impactor or cyclone. So for this is very, very important figure to understand how we at NPL, how we do the calibration or testing of this impactor or cyclone, whether it is really 2.5 impactor or whether it is PM10 impactor or not. So just to understand, I put the very simple graph here. You can see it's called the cutoff size evaluation. Cutoff size means PM2.5 is a cutoff, for example. So if here is the aerodynamic size of the particle from 0 size to 5 micrometer size, you can see. And here is the penetration efficiency. Penetration efficiency means the particles coming by this way and penetrate through this nozzle or this impactor and coming to the filter. So this is called the penetration efficiency. So if it is, this impactor is like a sieve, then 2.5, whatever you have a 2.5 particle, they should penetrate through sieve and then they should deposit on the filter here, right? So you will get, if you plot this penetration efficiency versus aerodynamic diameter size, then you will get, you should get, if it is the sieve, then you will get this kind of rectangle, this rectangle, right? But this is not the sieve. So what will happen? You won't get this rectangle. You will get this, the purple color, this curve. So that means these particles which you supposed to collect, you are not collecting. So you are losing this much of particles, you green one, and blue one, which you suppose not to get, you are getting here because it's not the sieve, right? So some particle, because of the size, some density or some other effect, you will get some particle which are bigger than 2.5, but they are coming here, and some particles which are lesser than 2.5, they are not coming here. So you are losing some particle and you are getting some more particle here. So that's why we can't estimate the particle at the 100%. What we do, we will just see that at the 50% efficiency, how much, what's the particle we are getting at the 50% efficiency, what's the particle size we are getting at the filter. That is this is called D50 or cutoff size. So what we do when we do the calibration of impaction or cyclone, we just plot penetration efficiency versus aerodynamic diameter. And then we plot at the 50% and see what's the size. And we do a lot of calibration. And because this facility is started in 2018, right? Calibration facility. So since then we did a lot of calibration and testing, and we got, almost 90% sets are out of this range in India. So we suggested how to correct their impactor and cyclone. So this is the situation, but we did some corrections. And for this, we have wind tunnel facility for PM2.5, PM10 sampler calibration. You can see this is wind tunnel facility we have at NPL. So we do the calibration. What the calibration is, just the penetration efficiency and aerodynamic diameter. So we plot this and we will get the D50 or cutoff size of the cyclone or impactor. So this is our wind tunnel facility, you can see here, and then we plot like this, and we'll get 50% efficiency, 2.5 of many cyclones. And we have, this is what we have. It's this one is our standards. So we got two standards, very sharp cut cyclone and winds impactor, which has the 2.45 micrometer and a 2.54 micrometer, the cutoff size. And this is the schematic of our wind tunnel. What we have a filter here, HEPA filter. Then we have a particle dosing system here. Then, because of the dosing, they can mix here, and then we'll get the particle laden air. That means particle cloud here. And then this, this inlet system can put it here in the text section, and then we can see if say 100 particles, PM2 particles are here, then we should have a capability. This inlet should have a capability to get all 100 particle inside. And then at the B point, we should have 100 particles. Sometimes it's not possible. Sometimes we have a 98 or 97 particles. So it's okay, no problem, but not less than 98 particles. So 2%, plus minus is okay. And after that, we have a here, it's a impaction or a cyclone. So then at the C point also, if we have a 100 particles here of 2.5, so impactor should get 100 particles. It should be capable enough to cut this. So sometimes when we have a 1000 particle of different size, and out of 100, out of 1000, 100 particles are 2.5. So only 2.5 particles, 100 particles should come here, and 900 particles should remain here, right? So this is called the how we do this kind of calibration. So this is the turbo pump. We suck the air through this, and then this turbo pump, we can change the speed also. You can see here, and then this dust can go outside the room. It's in our rooftop, so we can just send the particles to air. Okay, so now problem. Because we use this design, which is recommended by US EPA, recommended by UN, or recommended by European countries, we don't have our own standard. So what will happen? You can see when we use this particle. So if we have a very high concentration of particle, right? This is the winds impactor. So air is coming by this way, and we have a impaction plate. So bigger particle will stay here. PM 2.5 will go by this way, and then we can deposit on the filter here like this, right? But if we have a very high concentration of particles, we will see, this kind of particle deposition here. And when the particle deposit like this, then what will happen? The distance between this nozzle and this plate will change, because we have a particle hump or particle mountain type of structure here. So because of this structure, this distance will change, and then cut point will change. And as we get a more size, more up, then what will happen? The more bigger particle will stay here, and we'll get the less particle. On the other hand, because this hump, what will happen when there is some winds or something, so there is a chance that this hump or this mountain particles can again resuspend or emit from this source, and will get the overestimation. So this kind of problems we always saw in measurements. So this design is not good or not fit for our own condition. So we need to design as per our condition. So we suggest that we should have a multi-nozzle system. And also, if you look at, this is just for mass measurement, but if we want to get, because its size is very small, right? So if we want to measure many other chemicals, like Ashutosh said that we have a many impact of nanoparticles, and also it can be harmful for lungs because of the chemicals. So if they have some plastic or some other material, so we need to do the testing, chemical testing of these particles. So when we do some chemical testing, that means we need a more material. So when we need a more material, then this simple or smaller size or low volume sampler is not good enough, because they have only 16.67 liter per minute flow rate, very small size of filter, and also single nozzle. So we have a lot of inaccuracy when we have a very high concentration of particles. So to avoid this, what we did, we developed high volume sample. So now we can use 8 into 10 inch filter. So from low volume, we can just use the 37 or 47 mm filters, but now we can use 8 into 10 inch, it's a bigger one. And also for mass accuracy, for example, here you can see for low volume sampler, right? If I say the flow rate is 1 meter cube per hour of low volume, then in 24-hour samplings, I can suck only 24 meter cube air. That means if the concentration of PM 2.5 particle at the upper limit of the regulatory limit, like a 60 microgram per meter cube here, then in 24 hours, I can collect 1440 microgram, right? So in grams, it's 0.00144 grams. So for this, the balance I need, which should be 0.1 milligram accuracy. So the readability should be at least 0.1 milligram of that sampler, but that balance. But unfortunately, in most of the monitoring station, we don't have this much of sensitive balance, but we have 10 milligram sensitive balance. So for that, if I use high volume sampler, then high volume flow rate is, as I have mentioned here, okay, it's it's 1130 liter per minute, so it's 67 meter cubes per hour. So if you use this in for 24 hours, so you'll get this much of meter cube volume of air. And in that, if the concentration of particle is 60 microgram per meter cube in air, then we'll get 97632 microgram on the filter. So in gram is this. So for this, I need 10 milligram sensitive valence. So it's okay. So high volume sampler is okay, but of course it has also some drawback that you need a big filters and also the big space because it's a little bigger than the low volume. But accuracy is more, and you can use it for all chemical analysis. Like if we want to see what's chemical composition of air, that we can do. So we develop this high volume sampler, you can see, and we compare with the already existing sampler in market. In market we have a TISH, the American high volume sampler. So we compare. So you can see here is the red one is the TISH one, and blue one is ours. So ours is much better, and also cut point. If you look at the CSI NPL particle cutoff size, sampler cutoff size is 2.52, whereas for TISH is 2.43. So in our case, it's always good, and it can work for even 500 microgram per meter cube because it has a multi nozzle. You can see the multi nozzle. 140 nozzles are there, so it's very, very good for Indian condition. So this is the sampler what we developed, and this is TISH and this is ours. We compare and we got a very good results, and this technology is transferred to one industry. So we compare this PM 2.5 TISH. This is ours. This is TISH. You can see the very good comparison. With also BAM we compare and we got a very good results. And this technology is transferred to some industry. So TISH has this structure, and again the problem is the same like I said, this one, because they have only 40 nozzles and we have a 140 nozzles, so we can avoid this kind of problem. This is ours. So this technology is transferred to one company and they are making it. So now it is available. So this is one thing we did. So calibration method, testing method we developed, and also we developed this technology. And now we are on the verge to transfer one more technology which is related to BAM. And this is just the paper, because when we do some work, we got a patent, we got a papers, we also do some PhD of our students. So this is US patent already published and papers. So for BAM, what we did, again, this is interesting to show you some results. Like in the beginning, we said that we have a problem in November and October. So this is the picture of 2017. I have a recent pictures also. So November 4 to 14, you will see, this is Delhi. So in Delhi, we got a lot of smoke. This is the smoke particle, and this is the red spots. That means we have a biomass burning practices here in the Punjab and northern side. So the plume, this smoke plume is coming, and you can see here is the New Delhi. So we got a blanket of this plume or this smoke, and this picture is taken from the satellite. So that means this is the picture. So yeah, we have to believe on it. And then this is the cutting of the paper. So they say that, yeah, this stations, the government station is very close to NPL. NPL is in between this, right? So they say that it's 7480 and 803 microgram per meter cube, right? The concentration. Here they say 494, here they say 592. And if you look at here, this is 803 or 748, but here is 1400, this one. And the distance, if you look at, it's just 3-4 kilometers. So it's almost double, right? So sometimes it's very difficult to believe Of course, this is plume. So you can see the plume means it's not homogeneous. The concentration of particles is not homogeneous. So there is a chance that they have some heterogeneity, but it's not like a double, right? So anyway, that means there is some local influence as well, local influence, or maybe some problem in the measurement. To better understand these issues, what we did, we also measure at NPL. So here when we measure, it's in between this. So you can see at that time the concentration was 332 plus minus 17 microgram per meter cube. And here when they measure 500 around, we got a half, 245 plus minus 12. So this is all calibrated, traceable. Then in the next day again the same, we got a less concentration. Yeah, here they got about if you look at 332, here is a very high concentration. Here is very high concentration, but we got a 366. Yes, 316 plus minus 16 microgram per meter cube. Here is again very high concentration. So this is in comparison, but this is the total average you can see for 24-hour average. So this is very high concentration they have reported, but when we check, our concentration is lower than what they have reported. Similarly, here you can see, the concentration we measured, and we try to find what's the problem in BAM. So this is BAM. This is when we open the BAM, you can see this is in our lab. We have this, and air is coming by this way, and we have a filter here. You can see this is the filter, and this is the unsampled filters, and this is the filtered sample. So when we do the filtration of when we got the sample, you can see the black spots here, right? So what happens when we checked and we saw that, of course, we have a heater, and heater temperature is 70 degree. And in US, they reported that 70 degree, it's enough, because if you make more temperature, then what will happen? The VOC will also evaporate. So you'll get less particle then. You will underestimate the particle concentration. So it is better to use 70 degree temperature here. And but in our case, sometimes we have a very high humidity, 80% or 75%. And in 75 or 80%, this 70 degree temperature is not enough to evaporate all the moisture. So we always get moisture on the particles. And when we have a particle, wet particle, then we always have overestimation. So this is the one of the major impact. And when we have a biomass particle, you can see the black particles here. So in black particle, of course, we have a black particle as well as organic carbon. And this organic carbon is water soluble. That means they can absorb the moisture. And when they absorb the moisture, then we always have the overestimation. So we got this problem, and now we're trying to solve it. So this is just equation I0 epsilon minus mu x, and you can see this mu is the attenuation coefficient, and this mu values is important. And this mu value, when we use this mu value, x is just the the density, mass density, but mu is important. Mu is the constant, and it depends on the particles. When we have a sand particle or salt particle, the mu value will change. When we have a black carbon particle, mu value will change. And US and other country, because they don't have a different lifestyle, we have a different lifestyle, right? In each season, for example, in winters, we use a different way to live. We are very different. So sometimes we use combustion burning practices in our garden or some compounds, but we can use very open burning practices. But in US, they don't have this much freedom, so they don't allow this open burning or this. So what I want to say that their air composition, the particle composition, is almost similar in all 12 years, because they don't have the particular source at particular season. But in our case, in winters we have a black carbon problem, but in summer we have a dust. So particle composition is totally changed, and then we have a mu value. It's totally different. And what we use the other country's instrument and this mu value is fixed, 0.7, 0.76 value, it's fixed. But in our case, it may vary from very low, like 0.4 or 0.5 to 1.2, 1.3. So site specific calibration is important to get a very good data. So for this, we are developing one calibration instrument as well. And we want that government should regulate this instrument, that every monitoring station should use this calibration instrument, and they should go for the intermediate checks, because all monitoring stations should be accredited. And if you go for ISO 17025 accreditation, intermediate checks are important to see the calibration. So, but they don't have, so far they don't have any means how they will do the intermediate checks for this beta attenuation system. And they have more than 1,500 instrument working all over the country, but they don't have the calibration or intermediate checks. So NPL tried it, and we got a technology now, and we are waiting that someone come and take this. So it is under patent, and once we get the patent, then this instrument, and it's the whole world, nobody developed this. So we are the first who developed this instrument. So this is again the same, the filter tape, and same thing. So what I said, we have confirmed it, this is beta attenuation value, and this is the gravimetric value, gravimetric measurement, primary method values. And you can see when we have a low concentration, like US in other country, they have a very low concentration, then the slope, these values are very close to the slope, this 1 line. And when we have a high concentration and a moisture, then it's a problem. We have about 30-40% overestimation. So this is the problem we have in our ambient air quality PM 2.5 measurement in India, because of this instrument. It's not calibrated, not site specifically calibrated. We use mu value from the supplied by the other countries, and also the calibration issues. We don't have the calibration issues. We have calibration issues. We don't have any calibration way how to calibrate that. So this already, we published this method. So you can see when we have a very high RH, 80%, then variation is too high, and also it's always overestimation, you can see. But when we have a low concentration, about 120, generally in US and other country, it's very, very hard to get more than 50 microgram concentration, even 40 microgram. So for them, it's okay. But in our case, always 300, 400. So, it's a problem for us. So this is already, we published these papers and research. This is again the same thing. We try to make the calibration, so site specific calibration. So when we have this much of difference, when we do the calibration, we can reduce this bias. So this is what we have proposed. Apart from this, like people say that, or Ashutosh sir just said in the beginning, that we are looking for some method, some instruments which can be used for their legal metrology purpose. So for legal metrology, yes, they need many VOC sensors. We need gas sensors. They need some particulate sensors. So we have this facility to calibrate them. And also, but the problem is we need to develop our own sensors which can sustain in our condition, right? So we are trying for particulate matter. So in that, this sensor can work for a very wide range, say for 10 micrometer to 500 micrometer. So some of the results we have, but yeah, it's the question. It's a matter of the patent. So I cannot show right now, but I hope that in next 6 months, if we get time, then I will come again and show something results, something good results for the sensors to you. So we can have a very small sensors. We can put it in our homes or in our offices to see what's the concentration and what's the size, like a nanometer or the micrometer size. So accordingly, we can take the measures. and protect our health as well as our conditions. So finally, I come to the conclusion. So at Gas Metrology NPL, we prepare and disseminate gas standards, and the available standards are air quality standards and greenhouse gas standards. Recently, we also are in talk with PTB Germany to make the energy gases for hydrogen, for CNGs, and for also biogas standards. So I'm not sure, how much time it will take, but very soon, or I hope that in coming years, we will have the Indian standards for hydrogen, also for CNGs, and also for biogas. There is an open opportunity, as we talk a lot, under Make in India program to develop air quality measurement instruments. So I just show one few examples, but it has a huge opportunities. There are still several issues in PM measurement. As I said, in BAM, we got some problem. So we try to solve this. We got some calibration method and also intermediate checks method. And I hope that within 1 year, the industries or the monitoring station should have this calibration system. So at least we'll get the correct data. Need to develop technology and instrument meeting Indian ambient condition, as I said. Also need to redefine standards, because our standards, what we did, we just copied from the other countries. So we need to redefine it as per our own condition. So this is my submission and my conclusion. And with this, I think time is still, but yeah, we can have some questions, and whatever you suggest, Ashutosh sir will follow after that. Thank you
Thank
very
you
much.
very much, sir. Thank you for this brief and wonderful, interesting session. I would like to request, first of all, our Joint Secretary, sir, if you want to add something.
Uh, I, congratulate Dr. Agarwal for having spoken so well, and his, the talk in the very beginning was very lucid, very simplified for a common person to understand as to what exactly are the problems. And he has also illustrated the gaps which are there in our instrumentation methodology. There are no standards per se. There is one standard which probably we made in 2009, which is uh, likely to be revised soon. I understand that should be done soon. From our perspective, there are two, three things which I still am to understand as a maybe a policy expert, and we need to take them forward. One is, who actually authorizes these measuring instruments? One of the points which he probably mentioned are the different newspaper reports, somebody saying the pollution level is so and so, and someone else is mentioning the 2.5 or PM10, suspended particles in air in maybe northern India or Delhi being very different. So I think there is a proliferation of instruments which have possibly being used for measuring these particles. As he rightly mentioned, they are not calibrated and there is no traceability of that particular information. So there needs to be some discussion with the Central Pollution Control Board and other authorities as to how to regulate what are the measuring instruments, especially for these aerosols, and of course the gas particles, and what exactly, who's calibrating and authorizing them, that these are fit to be probably giving measuring measurements, and then maybe reported in the press about it, because it creates a very different impact. Of course, there is air pollution and it needs to be measured. And I think the situation is much better than what it used to be some 25, 30 years ago, when we used to drive on a scooter and entire your shirt used to get black, and with a lot of black particles you could possibly see on your shirt. So it's no more that kind of a condition, and certainly all efforts to NPL and all our central pollution control agencies. But then there are a lot of other things which are now emerging as industrial pollutants or aerosols, and as what there are challenges of plastic particles getting into the bloodstream, what Ashutosh mentioned, and there are a lot of health hazards and other hazards which have been rightly pointed, vitamin D deficiency and so. So on a policy side, there are two or three things I've taken. One is this particular knowledge of maybe chemiluminescence methodology of NO2 measurement or SO2 measurement. These need to be taught in class 11th and 12th. That's what I understand. Maybe our pollution chapter, where we teach a little bit, that syllabus can be marginally expanded. Ashutosh can possibly write in consultation with Dr. Agarwal to NCERT, and we
Yes.
can also write to Ministry of Education and HRD about this. So I thought that this is extremely important, the way he explained these small explanations and possibly the process that gas chamber and other things to measure SO2 and NO2, and why this particular machinery is not being made in India. We're importing some 200, 300, and these are largely being utilized by the government and the state government, maybe pollution measuring agencies. So the industry needs to come up. There has an industry interaction is required there. There is maybe a licensing issue to what are the measuring instruments which are proliferating in the country. And of course, there is a standards issue which falls within the domain of the BIS and of course our department. We need to take this forward. So these are a few points for us to possibly look into. Of course, an excellent, maybe lecture and very knowledgeable. I sat through the entire thing, was listening very closely, and then he also measured about one particular maybe gravitas or some methodology instruments which regularly measured. No, the other option, which beta one, which needs to be manufactured. So we need to take this forward to the industry, to FICCI, ASSOCHAM and others, and of course, whatever is possible once our set standards are revised, because they are coming up new standards as Dr. Agarwal mentioned. Once they are there, we need to take it up with the industry to develop indigenously, and because this is going to only grow, and every city or every municipality needs to require this kind of an instrument, and it will be extremely expanding knowledge and field. So the BSc students and class 12 students also need to be taught about it. And of course, it was great knowledge and a very good lecture. So I thank the expert for giving us this extremely detailed and very simple and lucid exposition on air pollution and the gaps in instrumentation. Thank you, sir.
Thank you very much, sir, for your kind and knowledgeable words. We are really thankful to you for your great support to the legal metrology. And I would like to thank Dr. Shankar Agarwal Saab, who has made this topic very clear, very easy. Sir, we have large number of questions. I will take it later on. Just I would like to request Santosh ji, can we take the photos of all the participants in the let's say in 4-5 posts?
Okay, sir.
Please make all of them video on. Sir, we want to make it tweeted, and when we are tweeting it, then the participants can see they were present at that time. And now, sir, I have already shared our Twitter handle as well as WhatsApp, Twitter, Facebook, and this one another Instagram. I have shared all this in the group, and but your I think you have not opened your video on. Kindly on your video. I am removing all of us from the stage. We are not able to see the videos of others. संतोष जी few more.
सर 1 मिनट से मैं बना रहा हूँ, पहले सुना रहा हूँ सभी को
जी. You take the photo, please. I am not able to take now.
हाँ तो 19-20 उसको अलग करेंगे।
Santosh ji, kindly switch off the mics of all.
Sir, photograph cannot be taken, sir.
I would like to request all the participants to kindly use our Twitter handle and retweet and like this. This is Jago Grahak Jago. And because you will get a lot of very beautiful and informative information, useful information for our daily use of the Department of Consumer Affairs website on this Twitter handle. And certainly it will help you out wherever you will go on in the market, or the technical information which a person should know in India. These are all informations we used to have a lot of tweets on a daily basis, large number of information you can gather, and kindly make it, retweet it, like it, and you can also use the Facebook handle we are doing, and the Instagram. Santoshi, is it done?
Sir, we cannot get a video, sir. Video, or otherwise we cannot take the photo also, sir.
Maybe you cannot take because he is taking.
Okay, sir.
Santoshi, done?
Wait for a minute.
See, my name is VG Ramesh Kumar, sir, Deputy Commissioner of Labor Headquarters.
Sir.
And I was just a trainee from 92, batch of inspecting.
Oh, very good.
This,
okay, sir. Thank you.
Also, sir.
Thank you, sir. Nice to hear you. Sorry, sir. I am keeping you holding. I am sorry.
Yes, sir. All done, sir.
Done? Thank you. Thank you. Thank you very much. Now, Dr. Shankar Gaul, sir.
Yes.
Sir, can we take few questions, please?
Yeah, sure, please.
Just for 5 minutes?
Yeah.
Sir, few of them are asking for the presentation. As soon as you will share me, Santoshi, kindly check, because few of the participants have not received the certificates of maybe 2-3 last workshops. Kindly check it. If somebody has not received, kindly send an email or a WhatsApp to me. We will check and we will issue the certificate. There is no problem.
Definitely. Sir, we will issue by tomorrow.
Yeah. Sir, why parameters are increased in cold season?
Cold season, yes. Yeah, in cold season, basically we have mostly biomass burning practices more, because to fight the cold, people use this biomass burning, and even sometimes we use this garbage, and also meteorology. Meteorology means our planetary boundary layer height, where we have mostly gases and particles. It becomes, in Delhi especially, it's become even less than 50-meter height, just 50 to 100-meter height. Whereas in summer, it is more than 500 meter or sometimes 1000 meter. So boundary layer means it's just like a cover. So if the cover is, you have a one ball and one cover. So if the cover is down, then whatever concentration you have, it's more, right? And if the cover is up and it has a more height, then you have a diluted air. And also in winter, especially in Delhi and other region of India, the wind velocity is less if you compare with the summertime. So if the wind velocity is less, then again there is a problem of the ventilation. So meteorology as well as sources plays major role. Sources are become very high manifolds, and meteorology, especially wind velocity and planetary boundary health, is less, especially in winters. So we have this pollution problem. So this is my submission. And if you look at the NCR region, this per my understanding that in NCR region we have a many surrounded villages and small cities where especially in winter people use biomass burning and cow dung for their to fight the cold. And instead of this, if we can provide them the biogas, they have a very good cow waste. They have in villages too many cows. So if we use biogas plant and central biogas plant, and using this central biogas plant, if we can supply the biogas to each and every house, I think we can solve this emission problem. So we need to think, and I think we have a technology now to get a pipeline for biogas as well. So we can use the very good use and fertilizer we can also make, and also we can use this cow waste, and also we can reduce the emission. So this is we our just finding. Sometimes we have some research on this and review and survey. So we found this kind of findings. So I think this is the important thing for, especially in winters. These two parameters, meteorology as well as the sources.
Thank you very much, sir. Sir, there are a few more questions. What I will do, I will send you WhatsApp, and then we will reply in the groups or in email. So with this, because now time is over, and I would like to thank all of the participants, Professor Shankar Agarwal Saab, our Joint Secretary Saab, and all the participants who are having a close relationship with legal metrology and are participating in this program. With this, I would like to thank all. Thank you very much. Thank you, sir. Thank you.
Thank you very much.
Thank you.
Thank you.